So I think that we're live. There's nobody in here yet. So Eric, maybe you can try joining in and then. But that's only seeing it on YouTube. You might have to do something else to actually join it. If you click at the top, that's weird. I don't think you're in it though, because your camera is not active, and I think you've got to go to the page for the event, maybe. What if you go to Hangouts there? Here, let me try to invite you too. Let me try to invite you. Sorry guys, just a second. Trying to get Eric in as well. Okay. Well, thank you very much for joining in. In this Hangout, we're going to be going over some basic concepts in Haskell with Eric Jones, who's one of the Stack Builders developers. He's been doing some development for client projects for us in Haskell, and he's been helping to train some of our staff in Haskell as well. So I'm looking forward to seeing his presentation.
Having some technical difficulties, but I think we're ready to kick it off. So, Eric, go ahead.
All right, so it's good to see everybody here, and today we're going to have an introductory Haskell workshop. Uh, some of the things that we're going to go over is what Haskell actually is, why you would actually want to use Haskell for your production projects. We're going to go over some neat things that you can do in Haskell that you probably can't do in other languages that help you fulfill your clients' desires. So I guess we'll start. So what is Haskell? So Haskell is a general-purpose modern programming language with a strong type system and laziness. I guess that's how most people would actually describe Haskell. It's a purely functional programming language. And these features of Haskell, along with others, help us get work done faster than we normally would and in other languages. So I guess all else being equal, if we're just trying to choose between a language for a greenfield project, maybe Haskell would be the right choice. So I guess first we're going to move into what Haskell gets you. So I guess we wouldn't actually be looking at Haskell or even considering Haskell for use if Haskell didn't improve development speed. As consultants, and I spent some time as a consultant, one of the things that we're looking for is improved development speed. And we're not just talking about improved development speed initially. We're talking about sustained improvements in development speed. I mean, sure, we can use the easiest language possible, and we can hack together a bunch of stuff. But what we want to do is we want to actually have a fast or rapid development rate at the beginning. We want to have a fast and rapid development rate in the middle, and we want to have a fast and rapid development rate at the end of product life cycle. And the claim is that Haskell can deliver on these wants. So how does Haskell do that? So Haskell, it improves initial development speed by giving you the ability to easily create a domain language and have that domain language reflected in code. Haskell also offers easy refactorability. Haskell offers ease of test, and Haskell. One of the reasons why I use Haskell personally is because Haskell has an improved feedback cycle. Haskell has an improved feedback cycle over test, over even testing. And if you augment this with testing, you have even stronger guarantees. So I guess what we'll do is we'll start with a little bit of an introduction to Haskell, and we'll move on from there. So the first thing a person might want to do when they first visit Haskell or first start using Haskell is they're probably going to want to jump into the REPL and try Haskell out. So that's the first thing that we're going to actually try here. We're going to actually try to jump into a REPL and give Haskell a whirl. We're going to see what Haskell, we're going to explore some of the errors that Haskell gives you, because when you want to become familiar with a new platform, or you want to become familiar with a new language, one of the things that you're going to have to do first and foremost is come to some understanding of what errors the system is going to give you. Because in any language, you're going to be looking at errors a whole lot unless you're a perfect programmer, which I know I'm not. So the first thing we want to do is we want to jump into the REPL, we want to try some things, and we want to see if we can come to terms with the type of errors that we're going to get when Haskell, when things go bad. So the first thing I'm going to do here is probably, let me see if I could get this to where I want it. So, yeah, I guess that's good enough. So I actually use Emacs, which is an excellent editor, much like Vim or Sublime Text. So first thing I'm going to do is I'm going to start up a shell. From the shell, I can actually hop into a program called GHCI. GHCI is the Haskell REPL. You can, in modern versions of GHCI, you can type almost any command that you would type in a Haskell file, and it would be a valid GHCI command. So the first thing I probably want to do is I want to know how to import modules or import things. So to import a module in Haskell, what we would do is type the import command. And we can choose a module at random, and we can import it. So importing data.list will give us data.list. There's other ways that we can import modules in GHCI. One of the ways that we can do it is with a :m+ command. And I could import data.maybe. And as you can see, the prompt updates me with the modules that I've actually added. So because we don't actually need these modules, maybe I can remove them. So I removed data.maybe, and I'm going to remove data.list. Forgive. Okay. So now we're getting a little bit more comfortable with the REPL. One of the things that I can do with in the REPL is I could evaluate values. And this is going to be a nice learning experience for us when we press enter. I get 3. So let's see what the type of 3 is. The type of 3 is a number. Now that's a very general thing. Haskell is a very general programming language. What I mean is that you only have to specify as much as needs to be specified. And this is a very important concept in Haskell. So as you can see, we're actually making some progress in looking at type signatures in Haskell already. We're making some progress in looking at type signature already, only with and we've only looked at one number, 3. Now, what do I mean? We can specify things even more in Haskell. Let's say I have 3, and I want it to be more general than just say a number. A number is just a type of a type. A number is a type class, so to speak. We'll move into, I guess we'll explore that more maybe in later workshops. So one thing I can do with the numbers, I can specify it more. We can look at, we can get some info about the num class if we wanted to, and we can see that the num class has many instances, or at least 4 here. The num class can be an integer, an int, a float, or a double. That means that when we specify 3, or when we say 3 on the command line, we can choose one of these things that we want it to be. Now here, we didn't specify. So the REPL actually gave back the most general thing it could, said 3 is a number. But let's see what happens if we actually specify a little bit more. So let's see what the type of 3 would be if I told it that I wanted 3 to be a double. So of course it would say 3 is a double. And the printed representation of a double actually has a decimal point and a decimal place by default. Okay, so let's do some more interesting things with Haskell. But to do more interesting things with Haskell, I'm actually going to leave the REPL and I'm going to go into an editor environment so I can do more interesting things with Haskell and show why Haskell may be a tool that you would want to use for developing your applications. Let's see, do I still have these? Let's see that. Let's see if I have some projects open here that I can play with. Hold on. Okay, so what I have open here is a bit of a web application, but we don't actually want to look at that yet. So I'm going to actually remove a lot of this code. Now we're left with exactly what we want. We have a plain module here. Okay, stop. So we want something that actually builds here. All right. All right. Now it looks like I've got something that I can work with. Okay, so sorry for the delay. So what we're going to do here is we're actually going to explore a little bit of what Haskell gives you and why Haskell is a language you might want to use for your development. Now, one of the things that you want to do when you actually start start a project is you actually want to start building a domain language as quickly as possible. These are some of the concepts that are discussed in areas like domain-driven design. In fact, in my opinion, these things are just good development habit. One of the reasons why you want to develop a domain language is because you have a common language that everyone can talk about. And Haskell actually makes this quite easy. In fact, one of the things I can do in Haskell is immediately start out by building a small domain language. So let's actually get that started. So if we just pick a field at random, I don't know. Let's choose something that probably something very simple, but something that may seem a little bit useful. I don't know. One of the things that I used to do, you know, as an early college student and as a high school student who went to sort of like a technical high school, was I did electronics. So let's make a small application to model some electronic devices or some electronic components. And we'll see how we can build this domain language in Haskell and how we can move along quickly and establish terms that everyone can use, unambiguous terms that everyone can use, and how we can easily start from almost nothing and start to flesh out a little bit of an application here. And we'll see how easy it is in Haskell, and we can see why, you know, not only does Haskell allow easy refactorability because of these domain terms that are easy to create, it also, like any kind of domain language, improves you know, communication between developers. So the first thing I'm going to do is start with, I don't know, there's many options in Haskell. Let's start with the simplest gate, the simplest electronic gate that we could possibly have. So I'm actually going to start with a not. So as you can see, I really didn't do much. All I really did was specify a domain term. And the domain term is a sound Haskell entity right now. In other languages, we might have to do more. In other languages, we may need templates so that we can build, you know, large syntactic constructs like classes. In other language, it eases the burden of the syntactic construct. But in Haskell, we're actually quite concise. We said we wanted a you know, something to represent a gate, the simplest gate possible or not. And we were able to simply create that. If we go down here to our running REPL and we say something like, you know, what's the type of not, it will give back not. If we ask for some information about not, it will tell us where it's defined. Interesting thing is if we ask for the kind of not, it will give us a kind. It'll say that in order to create this type, all we have to do is specify one thing. So let's make a function that works on not. So we can make a little function that runs a component. So we're going to make a function that runs an electronic component. The only electronic component we have right now is a not gate. We also need a signal. And we're going to return the signal. So we created a not gate, but we don't really know what a signal is, and we haven't really. We don't actually know what a signal is. We actually haven't really discussed what a signal is. So our development environment should reflect the fact that we haven't actually discussed what a signal is. Now, conventional methods of actually you know, getting this type of feedback would be to first make a test, and your test should fail in a certain way, telling you that you haven't described what a signal is in any way, shape, or form. But I guess my claim, and I guess the claim of the Haskell community, is that the type system actually offers you that same feedback. So if we were to go and try to evaluate this, we'll see that a signal is not in scope. Now that was very quick. Now any compiler would probably give you that sort of feedback, but this is we're starting to see the basics of the feedback that a type system that this strong type system like Haskell actually gives you. We're starting to use something called a signal, but we haven't defined it yet. So at this point, you can go ahead and you can define what you think a signal should be. And just like any good test-driven developer would do, we do the simplest thing that will work. We'll do the simplest thing that can appease the type system. We'll do the simplest thing that can appease the compiler here. So I'll try again, and the compiler says that everything's okay, which means that I can move on.
Sorry, I think they can see you share a screen. Probably you just share the virtual machine. So probably you need to share all your test stuff.
Gee, I was going on for a second. Thanks, Sebastian. Wow. Screen share. This is what I want. Screen share. Okay, so I guess we probably need to let's back up a little here. So this is what I was looking at, and this is what I was talking about. Before we tried to use the concept of a signal before we actually had it, and we immediately get some feedback telling us that. There was no need to go through a build process or anything like that. The Haskell system, the Haskell type system, the Haskell compiler automatically told us that there was no such thing as a signal. So what I'm going to do in the spirit of test-driven development, or in this case, what some have called data-driven development, is I'm going to do the simplest thing to get to appease the type system. So now I just typed in data signal equals signal, which really doesn't mean anything except to us, the developers. But we have appeased like the type system here. So now I'm going to move into defining what I actually think what I actually think this should be. So, given a gate, we don't actually have the what a gate should be. So we'll talk about that in a little bit. And given a signal, we'll call it signal, and we'll call this gate not. And we don't know what a signal is yet. A signal doesn't have any constructors, so I'll just say a signal should be high. Maybe I would like to return low. And let's try again. Let's say given a gate, given load, I'll probably return high. So without thinking about some of the terms that I already described, I saw that what I had created so far was inadequate. The type system is going to tell me, or the compiler is going to tell me, that some of the things that I just did were inadequate. So I'm going to try to rectify some of my type signatures, and I'm going to try to rectify some of my data constructors to be in line with what I just created. So at first I thought I needed some things. I needed just a gate and maybe just a signal, but now I've seen that's not correct. I've seen that doesn't really fall into line with what I wanted. So what I actually want in this case is maybe a gate, a Boolean gate. So I'll make this a gate. A signal's okay, but signals seem to have two options. A signal could either be high or low, and it could return another. In our function, returns another signal, either high or low, which means that we need an algebraic data type. A signal that can either be high or low. So it seems as if we appease the type system by making those modest modifications. And this is how we actually incrementally step through a Haskell program. We actually start to create what we think we need, or the domain terms we think we need, and those domain terms will evolve as our thought process evolves. Those domain terms will eventually solidify. Once those domain terms actually start to solidify, and once I have a working program, that would probably be a good time to add a test. So some people, or I guess most of us, have been raised to believe that test-driven development is the right way to do things. And to tell you the truth, I believe that test-driven development is the right way to do things for many reasons. But as Kent Beck said in a blog post that he released I think maybe last year sometime, probably about 6 or 7 months ago. He said that when he tried test-driven development in Haskell, it simply didn't work. One of the reasons why I think test-driven development in Haskell wasn't working for Kent Beck is because types actually rule the day in Haskell. You're not going to get very far without writing a type. You're not going to get very far without explaining to Haskell what you're talking about. And once you know what you're talking about, once you know your domain terms, then you could actually move into a test. In fact, once you know your domain terms, then you can actually start to move on with higher level development. So as we can see, just using the type system alone, we derived ourselves a nice little function. And maybe as we move into let's say more complex things, we might find that these type definitions aren't very adequate. And the first person or the first thing that's going to tell us that our type definitions are outdated or need to be updated or need to be advanced in order to move on with development is the type system. And this is one of the reasons why Haskell encourages rapid development. Now, one thing I want to talk about is pair programming. I mean, and we can't really divorce Haskell development from development as a whole. That's one of the mistakes I see, quite frankly, in the Haskell community. Haskell seems to maybe divorce itself from all the other advanced things that are going on in the programming and development world. Rarely do we hear people talk about Haskell and type-driven and test-driven development. Rarely do we hear people talk about Haskell and pair programming. Rarely do we hear these things. But as more and more people start developing in Haskell, it's inevitable. All things that rise must converge, so to speak. So one of the things that I'm going to hit on is modern development practices with relation to Haskell. Now, when you pair program, you're pairing with another person. And the things that we just went over, like domain terms being defined as data types, these are the things that keep you in sync with your pair. These are the things that keep you and your pair talking about the same thing. And since they're so clear, and since they're so evident, and since they're so integrated into everything that you do in Haskell, your pair and yourself are less likely to get out of sync. So if I was sitting here with a pair, we would be talking about gates and signals right now. And that's pretty much the only thing that we'd be talking about. There's really nothing else to get in the way. We don't really have to talk about inheritance. We don't have to talk about whether something should be, like we should have a superclass called gate and a subclass called not, and the rest of the gates that we might, consider. We don't have to really think about those design decisions. Those design decisions in Haskell don't really exist. Everything is pretty straightforward. We just pretty much design our types and move forward. So let's see what we have here. Let's try to run this component in the REPL. So I have two types, only a gate and a signature, and I said that run component takes a gate, and the only one we have is not. I also said we have signals, and the second thing this component takes is a signal. So I'm going to give it a signal of high. So when I run this component, the type system is going to tell me that I don't have an instance to show for the thing I'm trying to return. So basically, what the Haskell compiler or the REPL told me is that it doesn't know how to show. It doesn't really have like a so-called show instance, which is pretty much akin to a toString method in other languages. So I'm going to go ahead and automatically derive one to appease the type system. So now I have what most people would consider a toString method, which is pretty easy, which was pretty easy for me to do. So as you can see, I'm failing very fast by using the type system and using the REPL like this. So let's try that one more time. So my component actually works. Now that's very simple. One of the things people might be saying right now is that, okay, that was a very simple function, and of course as a simple function, we got it to work really simply. However, in Haskell, all of your components should be simple. Everything you make should be simple. Complexity comes not through the construction of things. Complexity comes through the composition of things. The composition of things should be easy. With the things that help you combine your simple components should also be simple. And as you'll see, we'll be able to build up actually rather complex systems by simply combining simple components. So we can't really do much with a NOT gate. We can't do anything with an inverter. The only thing that but one more component, if we add the addition of one more component, we can do anything that a computer is capable of doing. And we actually have a choice. We can make another gate called AND. Or we can make a gate called OR. So let's make AND because I like conjunction more than I like disjunction. So one of the things that we can do now is augment our signal, our function. So an AND gate is actually a two-input gate. An OR gate, a NOT gate is a one-input thing. So we'll account for that by saying that a NOT gate ignores. So what we're going to do here is we're going to say AND. And AND has combinations of things. So if this is starting to look like a truth table, it's because, in a sense, it is. So we'll start, if N has any input that is low, then the resulting signal is going to be low. Okay. Let's say that signal that is low, and the resulting signal will be low. Okay, so now we added an extra signal, and we said it was N. Now, normally, if we in normal situations, we could probably define we can just use AND as if it existed. That's probably the easiest way to go about it, is to just use AND as if our new gate as if it existed, and the type system would definitely fail. The compiler would definitely fail telling you that that's not that doesn't exist, and you can go ahead and add it. Since I'm pretty used to Haskell, I actually just went ahead and put that in there. So that's one of these are. Let's go ahead and try our run component and see if everything's okay. So one component, and I want to give it low and high, and see what I get low. If I give it high and high, and give it high. So as you can see, it's really easy to start defining small domain languages and small sort of interpreters for that domain language in Haskell. So these are this is one of the things that gives you rapid development. But as you can see, there's really no composability here. There's really no composition. So just making enumerations of things and making, how can I say, functions that just take that particular data type and run over it is not a very good way to do things in Haskell. So what I'm going to show here is I'm going to move into a little bit more of an advanced approach to doing the same thing. Now that we're a little bit more comfortable with Haskell, and now that we're a little bit more comfortable with the REPL and so forth. So instead of making what a gate is now in this example represented as an algebraic data type. Now, algebraic data type is pretty much either a sum type or a product type. Here we have an algebraic data type, and we're just listing out what a gate can be. But that's not very composable. In fact, everything we have here is not very composable. So what we're going to do is we're going to change this scheme a little bit. And this is going to try to, what I'm going to do here is going to drive home a little bit of the point of how refactorable Haskell is. So I'm going to do, as we can see, our approach is a little bit limited. So what I'm going to do is I'm going to change the representation of what a gate is. One of the ways I'm going to change the representation of a gate is I'm going to make a gate a type class. So I'm going to say gates. So give me gates. I'm going to take gates. I'm going to take gate signal. And I'm going to return the signal. And I'm going to pretend that the only gate I have right now is not. And I'm going to make some data called the gates. Data called not. It's going to be not. Let's go ahead and move signal. I'm going to move signal out of the way for the time being. I'm going to make class. A. It's just going to take pretty much a signal. Alright. So what I just did is I tried to make my system a little bit more modular. I tried to make my system a little bit more composable. And what I did was I defined a type class. I said, instead of making my gate just pretty much an enumeration of things, I'm going to make my gate a class of things. So we have pretty much a new class called gate, and the only thing that really defines a gate is the fact that it has a method that you can run on it called run component. So I guess this is as close to object-oriented design as Haskell will actually get. But most people wouldn't consider type classes akin to anything object-oriented. In fact, it has nothing to do with the class. We might be able to explore that maybe later in other workshops. So let's see how we actually use this newly created type class. Actually, what we want to do now that we created a type class, after we create anything, you want to see if it actually works. And then, as you can see, the system actually accepted our class definition. So let's move on and make an instance of that class. So instance gate not where. So if that was done correctly, then we should have a new instance of gate, which is not. So let's see what it says. It says we don't have our signal constructors anymore. And I totally just deleted that. So let's remake our signal data. So we still need our signal data, and that's going to be high or low. Let's see what it says. Gotcha. Okay, so one of the things I just did is I had a lowercase name where I wanted an uppercase name, and the system automatically came back within probably less than a second and told me that wasn't the right thing to do. And it did that as I further specified my program. Now that's one of the things about Haskell that some people love, and I've read complaints about this very feature, which I think is probably one of the most golden things about Haskell. Your system has to be consistent. Your system all has to make sense together to a certain degree. If you do anything that makes your system fall out of sync with, and if you write a new piece of code that makes an old piece of code fall out of sync, you'll know about it immediately. To me, this is one of the biggest advantages of Haskell, is that your system is going to let you know if you wrote something that doesn't make sense with something you wrote before. When you write something that doesn't make sense with something you wrote before, there's a name for that, and it's called a bug. And a lot of people actually are beginning to realize that this feature of Haskell is a very valuable piece of machinery. This piece of Haskell actually catches bugs before they actually make it to your tests. This is one of the reasons why people say that the type system is, in a sense, more valuable than your test, because it catches bugs way before your tests actually get to them. And should you actually run your test, given you have these bugs, the type system will fail before your tests actually even compile. So this is one of the things that that really increases the feedback cycle that we talked about earlier. This is the things that we talked about that improve sustained development. One of the things that just happened here, one of the things that what it just happened here highlighted is that my system was out of sync, and if I was to publish this code, let's say for instance I was in another language where something like that would just work, it would probably fail on a test. It probably would fail at runtime, but Haskell actually caught it at compile time. The reason why in some systems it would actually fail at compile time is because what was there before was actually syntactically valid Haskell. It was syntactically valid Haskell, so it would actually compile, which it did before we actually further specified our system. So I guess what I'm trying to say here is that if the system finds your program logically sound, you have a higher probability that another programmer would find your logic, kind of sound and consistent. And this is one of the things that make Haskell easy to refactor. So let's move on. All right. So it actually liked what we have here. So now we have a gate and we have a class called gate, and we actually have an instance of this class called not. So let's see if we can actually do that now. So let's see if run component is available. So run component is available. Run component is the type of thing that takes a gate. As long as it's a gate, it can take a signal and it can return a signal. So let's go ahead and do that. Let's say run component. And let's give it a gate. So I'll give it not, and I'll give it high, and just like, well, of course. So that seems to work. Let's get back up to speed by making another instance. So let's get back up to speed by making some more data. Now let's do things a little bit more modular than we had before. We'll make an instance of gate, which is n. And say here. Go ahead and define our run component. And we'll say hi. Let's say that's hi. Let's say run component. Load anything. Actually, the only case in which you'll actually get high is when both are high. So we can just say low there. Now, I think that's okay. I mean, it looks perfectly okay to me. So what I'm going to do is I'm going to compile it, but my compilation failed. So let's go and dig a little bit deeper and see what happened. So it says, could it match expected type signal with actual type signal? So whenever we see a little arrow there, it probably means, function. So whenever you see arrow, think function. As new Haskell programmers, if you see an arrow, you can immediately think function. As you become more and more advanced with Haskell, you probably find other ways to identify functions, and these arrows won't tell you function anymore. But as we can see, we actually caused an error. It says that on line 18, we did something such that we were expecting a signal, but we actually were using it as if it took a signal. It was a function that went from signal to signal. So basically, the Haskell type system said, wait a minute, something's not right. Some people see this as a hindrance to development. But to me, it just told me that what I was thinking was absolutely just wrong. It told me what I wanted to do does not match with the rest of the system. It told me this at pretty much type check time. It told me this at compile time. In other languages, especially, of course, none of us could really escape JavaScript, this would have easily been accepted. And then we would probably have to find some way to flex this code in order to find out that there's a bug. Sometimes we can go on and develop some more and develop a little bit more, and we won't even actually get to the point where we can flex this code for quite some time. Maybe we're in some existing code. Maybe we're in some existing code where we can't really get to the point where we really can't get inside to test this actual combination. Maybe we can't get inside of a certain class or flex a class a certain way because this particular logic is too nested. And the client really wants what the client wants, so we're not actually able to come up with a good enough strategy to test this branch of code. However, the type system actually has you covered in Haskell. You do something that's inconsistent, and it'll find it right away. So this way, you don't have to get a bug in the tracker, and QA doesn't have to get mad and because he tried something and it didn't work. Your program's going to pretty much stay consistent. Your little edge cases are going to be reduced to a minimum. And what's going to happen is you're going to find you have a lot less bugs in your program. You're going to find that your development process is a little bit more pleasant. And this has a big impact not just on development itself, but on the pretty much mood and mentality of programmers. A lot of times, when I'm working on Haskell Haskell programs with friends, and I'm working on Haskell programs for clients, the mood seems to change when a person has to move from their nice, beautiful Haskell backend where everything can just be implemented in a small amount of time, and they don't really have to do anything but figure out the code itself. High-level code that doesn't have too many hacks to get things done. Like for instance, wrapping things in set timeout, which has nothing to do with your domain logic. Haskell. When you program in Haskell, everything's fairly straightforward, so it increases programmer happiness, as some Ruby programmers would like to say. Haskell increases programmer happiness. So let's go ahead and fix our little error here. So what the type system just told us is that we're misusing this thing. And if we go back and we look at the definition of run component, we see that the definition of run component is not being used properly. We're going to take a gate, any gate, we're going to give it a signal, it's going to return a signal. That's a little bit unfortunate because an AND gate has 2 inputs, but we said it has 1. So what we're going to have to do is we're going to have to augment this if we want this, if we want sort of this iteration of what we're doing to work. So that should work. Now, you know, I appease the type system by telling it that, you know, you can have 2 now. So let's see what happens. Oh no, there's more problems. What? So now it says on line 20, it says, yeah, on line 15 something went wrong. It says that on line 15 and line 14 something went wrong. So what happens is in changing this piece of code, I broke another piece of code. Now that's something that, you know, I was raised to believe that tests are supposed to cover. I actually changed a new piece of code to make it work, and an existing piece of code broke. Now, the normal process that I would use is probably go and run my test, and after a million and one tests ran, and after the test week took 15 minutes, I would find out something's broke. But here, we found out right away.
We should probably wrap it up in a couple of minutes left on the clock.
Certainly.
On the clock, and then push whatever else into the next workshop.
Okay, so let's just go ahead and rectify this little mistake, and we'll fix that. So just as before, we're going to say I want to ignore the second input when it comes to a NOT gate, and let's see what happens. Now I just appease my system. So without actually having to run a long suite of tests, without actually having to you know, get this blow up at have it blow up at runtime and debug it and have to look at it in the debugger, I actually took my system from, you know, an inconsistent state where I added code that where I added a feature that needed to be added, which made another previous feature fall out of consistency or pretty much break, and I was able to use the type system to bring everything into harmony, and I did that very rapidly by just reading some type errors. So the type errors shouldn't really be a scary thing. The type errors should be looked at as your friend. The type system should be looked at as your friend. Once you get used to Haskell, you'll never want to well, I guess I got to be careful here, but once you get used to Haskell, you're probably never going to want to go back to a system that doesn't have such a strong type guarantees. You'll actually start to feel that that sort of development is slow. You'll actually not want to do that. So let's kind of wrap this up here, and let's just go over what we learned. We actually saw a lot of things. We saw the how to use the REPL a little bit. We actually saw some of the strengths of types. We actually made a case for why Haskell is actually improves development speed. We actually made a case for how Haskell actually improves development speed by improving our feedback cycle. We actually saw how Haskell, we can use something that has been coined as data-driven development to move more quickly. And I think just with this little example where we just made 2 simple gates, really drove home a lot of points. So I guess I'll close with that, and I thank everybody for attending, and I hope to flesh out maybe this example a little bit further in up and coming sessions.